Okay, so here we are with Unit 8, lesson number 3. And we're going to finish up what we had started in lesson 2. We're going to look at the remaining 6 factors that affect reaction rate. And numbers 2, 3, and 4 are really easy to explain using the classroom analogy that we had talked about earlier. So let's go back to that analogy. So really, you can kind of, once you've copied this stuff, you can really kind of put your pens down and just listen. So if we go back to the classroom analogy, if you remember, we take our room, we remove all the tables and chairs. So we have that big empty space in between my desk and the lab benches in the back. And let's say we bring in 6 students and we blindfold them. And we have them walk around the room blindfolded. They're going to collide with each other, probably not very often because that's a relatively big space. So let's take a look at how does that relate to this. Well, increasing the concentration would be the same as if we said, well, instead of 6 people, let's bring in 6 more people. Now we have 12 people in the room. That would be analogous to increasing the concentration. And I think it's fairly obvious that if you bring in 6 additional people and have those 6 people join the original 6, now you have 12 people. What is going to happen to the number of collisions? Obviously, the more people, the higher the concentration, the more reactions, the more collisions that are going to occur, that is going to make the reaction speed up. So in general, when you increase the concentration, in other words, if you add more reactants, there's going to be more collisions because there's more stuff to collide with each other. The room or the container is more crowded. Pressure. How would we look at pressure? Well, we take the same room, we put the 6 people back in, we take the other 6 out. And then what we do is we take the room and we all of a sudden start to shrink the room. And those 6 people over a period of time are going to be forced into a smaller. So think of in your head is that the room is shrinking in size. So those people are being forced into a smaller area. You still have those 6 people, but if now let's say we make the room half the size, now those 6 people are in a room that's half the size as it was before. They're closer together. If they're closer together and they have less room to move around, that's obviously going to speed up the reaction because you're going to have more collisions because they're now in a much smaller room. The fourth one, the analogy is the same 6 people. We're not changing how many are in there. And in order to make an analogy for this one, increasing the temperature, if you remember, temperature is the same as kinetic energy. So how would we increase the students' kinetic energy? Well, instead of them walking around, we'd have them run in that room. Okay. Obviously, if they're running in the room, they're going to be going back and forth much more often. That's going to make for more collisions. That's going to speed up the reaction rate. Okay, so 2, 3, and 4 are relatively easy to explain using the room analogy. The next one, which is surface area, is a little bit more difficult. So let me go through that and I'll give you an example of what we're talking about. If you're looking at surface area, here's what we're talking about. Let's say, for example, we had a piece of chalk. Okay, I'm not a very good artist, as you can see. It looks like a cigar. Now remember, chalk is sort of like a pipe, right? And when we talk about surface area, what we're talking about is what part of the chalk is exposed to, let's say, for example, if we wanted to react this with an acid like vinegar, this would react with the acid. But what would actually react with the acid would be the particles of chalk that are exposed to the acid, which is the outside, the surface area. How can we increase the surface area? Well, if we took this piece of chalk and we broke it up into 2 smaller pieces, that's not very good because it looks like a completely different piece. But if we cut this piece in half, how does that increase the surface area? Well, you still have the original surface area, but now remember, you broke this chalk in half. So now you have this piece of the chalk, think in your head, if you snap this piece of chalk in half, you have these 2 now areas of the newly exposed areas that are exposed to the acid. Now you've increased the surface area. How do you increase the surface area to its maximum? Well, you would grind it into a powder. So material that's in a powder form is always going to react faster because it has much more surface area. And that's how surface area is related to reaction rate. The more surface area, faster the reaction. And you increase surface area by making the particles smaller. And the last one is one of the definitions that you're going to need to look up is a catalyst. And really all that you need to worry about right now is what a catalyst is, its definition. A catalyst is a substance that when added to a reaction, it speeds up the reaction, but it's not changed. In other words, the catalyst can be reused. So you have this reaction, you want it to speed up. Catalysts are used a lot in industry. An example of a catalyst that you probably already heard of are enzymes. Enzymes are catalysts. They speed reactions up, and they generally can be used over and over again. So a catalyst speeds up a reaction, and how does it do it? And this is something that you need to remember. It reduces what is called the activation energy. So that is an extremely important topic that you need to remember. So you need to know that a catalyst speeds up a reaction, and it does so by lowering the activation energy. I would include both of those as part of the definition. And we'll talk about what activation energy is later on. Okay, now what you see here is, and this is the end of this lesson, this is what we call a potential energy diagram, but we'll get into this later on. So that's the end of lesson number 3.